Now that we know how to rewrite from exponential form to logarithmic form and logarithmic form to exponential form, let's simplify some logarithms. Now, a logarithm basically is asking, what's the exponent? So let's just do the first one where it says log base 4 of 16. So this is a fancy way of saying 4 to what power will give me 16. Now you could say, okay, this equals something, I don't know, we'll call it x. And then we'll do a rewrite and we'll say 4 to some power gives me 16. So we're going to go through several of these by hand, even though we could use a calculator, Desmos, whatever, to figure them out. If we have the skills and the mathematical knowledge and the number sense to do this in our head, it's going to save us a whole lot of time. And there's also some things in here that we need to understand conceptually. So let's continue. 4 to what power gives me 16? So a lot of people just glance at it and they say 4, because 4 times 4 is 16. No. This is 4 to what power would be 16? And the answer would be 2. So basically I would need to say, well, 4 to what power is 16? That'd be 4 squared equals 16. You don't have to write that step, because what that really means is, we'll make that x. X equals 2. So 4 squared would be 16. So 4 times 4, there are 2 of them. All right, let's go to the next one. Log of 1,000. Okay, we've already covered this, but if there is not a base that is written, and there's your base down there, base in this case was 4. If there's not a base that's written, then it's a 10, and we can treat it like an equation if you want to solve it that way. And we're going to basically solve it. So 10 to what power would give me 1,000? So how many 10s would I multiply together to get 1,000? Okay, well, 1 10 would be 10. 10 times 10 would be 100. 10 times 10 times 10, there's 100 times 10, that'd be 1,000. So it took 3 of them to do that. So that's what this process is about, kind of understanding this. So here we go. Next one, log base 1/2 of 1/16, and we'll say that it equals x as well. Even though the original problem didn't say that, helps us to understand it better from that context. So 1/2 to some power equals 1/16. Don't make this harder than it is, okay? Don't let the fact that it's a fraction throw you off. Okay, 1 to what power is 1? Well, 1 to any power is 1, pretty much, right? So 2 to what power is 16? Let's do that. 2 to what power will give me 16? 2 to the 1 is 2. 2 to the 2 is 4. Again, times 2 is 8. Times 2 is 16. It takes 4 of them. So x would be 4 in this case. In other words, if you wanted to switch colors for emphasis, you could say that 1/2 to the 4th power would be, let's do it, 1 to the 4th power and 2 to the 4th power. 1 to the 4th power is 1, 2 to the 4th power is 16. Okay? Again, technology will do this for you. But why would you rely on the technology when you can fly through it very quickly, especially with something like this or this? Count the zeros in this case. Okay, let's keep moving. Switch back to blue. This is where we really need to understand this from a conceptual point of view. So 1/2 to what power, let's put it in parentheses, is going to give me 16. I put it in parentheses so it didn't look like I was just raising the numerator to the x and not the denominator. Okay, so 1/2 to what power is going to give me 16? Well, I'm a little bit confused. So the last one was 4, right? We turned a 2 into a 16 by raising it to the 4th power, so it's a 4. Well, let's just go ahead and say it's a 4, but it's not a 4. So let's just pretend like we're right, and we are right. It is a 4, but it's not a 4. So if I did that, then I would have this, 1/2 to the 4th power, and that would give me, we just did this a minute ago, 1 to the 4th, which is 1. 2 to the 4th, which is 16. So this is wrong, but it's actually right. Okay, so let's kind of go with it. 1/2 to the 4th power would give me 1/16. Let's tinker with other things. Perhaps, knowing the answer, perhaps if we change the sign, that would change things. And this is where, again, we're getting into some conceptual territory here that's going to help us understand things a little bit better. So let's raise this to the -4. So now we're dabbling with negative exponents, and we need to understand what those do. So I have 1 to the -4, and I have 2 to the -4. Negative exponents move things. They move things from wherever they are, numerator or denominator, and they put them in the other place and make the exponent positive. So let's rewrite this. I don't like negative exponents. I like to move them. I like to move it, never mind. Okay, numerator is 1 to the -4. It becomes 1 to the 4 in the denominator. Denominator is 2 to the negative 4. It becomes 2 to the 4 in the numerator. 2 to the 4 is 16 over 1. That is indeed 16. That's why the answer is not 4. The answer is negative 4. Now, if you wrote all that, fine. If you didn't write that, fine. I'm about to erase it because it's going to be in my way. But negative exponents move things. There is an explanation for that. I'd love to go into it. I might tack it on to the end of this video for those that are deeply interested in why that works. I might use that opportunity to explain something else as well. Okay, log base 4 of 1 is something. I don't know what that something is, but that means 4 to some power is going to give me 1. Okay, so here goes. Again, type it in the calculator if you want to, but I'm going to tell you, if you understand this one, you'll be able to crank some things out pretty quickly. 4 to what power gives me 1? I don't know how to tell you without just telling you. Anything, and I mean anything, there's an exception, to the 0 power is 1. Anything to the 0 power is 1. So if I had 4 to the 0 power, I'd get 1. If I had, you don't have to write that, but if I had 5 to the 0 power, I'd get 1. If I had stickman to the 0 power, I'd get 1. As long as, now we get tricky, you don't have to know all this. This is not going to be something that you're assessed on right now. 0 to the 0 power is indeterminate. So we don't know what it is. Nobody knows what it is. Desmos thinks it's equal to 1. I disagree. There are arguments all over the place because 0 to a power is 0. Something to the 0 is 1. So what's 0 to the 0? Who knows? So as long as this is not a 0, you raise it to the 0, you're going to get a 1. So let's erase, go to the next problem. There's a reason that's the case too. This is reminding you, hopefully, of some old exponent rules that you may have forgotten, like negative exponents or an exponent of 0, or in this case, I'll go ahead and say it, a fractional exponent. So I want to simplify log base 81 of 9. I'm going to make it an equation equal to x, and then we'll just solve it. So 81 to some power is going to give me 9. So I ask myself, okay, what can I do to an 81 that will give me a 9? Like, what can I do to this 81 to get a 9? You can divide it by 9. That's great. But what would I raise it to? Oh, I can't square it. I could square root it. Okay, so what I need to do is square root it. I need to square root this 81. So if I square root an 81, I should get a 9. I'm doodling here. You can leave this part out if you want to. So the square root of 81, well, that's the same thing as 81 to the 1/2. An exponent of 1/2 is a square root. So basically, my exponent is 1/2. So that is my answer. Again, logarithms are asking, what's your exponent? That's what they're doing. Okay, 3 more. Log base 3 of the square root of 3. Don't know what it is. 3 to some power gives me the square root of 3. Okay, now I'm going to do this one. You probably already know the answer based on the previous problem, but I want to do this one a little bit differently. Let's kind of stare at it for a second. If 3 to the x is equal to the square root of 3, well, let's rewrite that, because I just told you an exponent of 1/2 is a square root. So if I have a square root, I'll write it as an exponent. And I have 3 to the x equals 3 to the 1/2. I think it's fairly obvious. Now I'm going to do something here that is very legal, but I'm not explaining how it's legal. But basically, x is equal to 1/2. There we go. Why is it legal? Because of the properties of logarithms that is beyond the scope of what we're doing in this particular lesson, because we just learned logarithms as inverses. Okay, 2 more. Log base 5 of the cube root of 5. And I just told you that an exponent of 1/2 is a square root. So if an exponent of 1/2 is a square root, then an exponent of 1/3 is a cube root. So let's go. 5 to some power gives me the cube root of 5. Well, an exponent of 1/3 is a cube root. So a cube root has an exponent of 1/3. There we go. And using the properties of logarithms that you don't know, we can just do what looks obvious, and we are left with, well, you might know them, I don't know. Maybe you're watching this video just for fun because you like logarithms that much. Anyway, you get 1/3. Okay, let's do one more. I love this one. Log base 6 of the cube root of 6 all to the 5th power. Okay, so let's digress for just a second here and talk about the fact that exponent of 1/2, let's go to the next slide. An exponent of 1/2 is a square root. An exponent of 1/3 is a cube root. An exponent of 1/4 is a 4th root, and you're getting the pattern, right? So as I go back to this previous problem, I have a cube root. So I'm going to have an exponent of 1/3. But what about this exponent of 5? Like this extra 5. Let's do it. Okay? Equals x. 6 to some power is equal to, and this is just a rewrite, cube root of 6 all to the 5th power. Okay, fair enough. We still haven't figured out what to do with that 5 yet, but we're going to get there. So 6 to some power gives me, okay, well, this is 6 to the 1/3. I think we could agree that cube root of 6 is 6 to the 1/3. We just saw that same example here. But that is all to the 5th power. And if you have a power to a power, you'd multiply. Again, I've done this before, but if I had x squared and I want x to the 5th and I wanted to square it, I'd have x to the 10 because 5 times 2, 10, right? So I have the same idea going on here. Now it's gone. Where I'm going to do 1/3 times 5, and I have, well, 1/3 times 5. You're basically going to do 1/3 times 5 over 1. 1 times 5 is 5. 3 times 1 is 3. You have 5/3. That's what you really have. So I have 6 to the 5/3. So even though the cube root makes it a denominator of 3 in the root, in the exponent, that exponent of 5, just pure 5, means the numerator is 5. So let me reword that. Cube root, denominator is 3. That is your numerator. So if I have something raised to the 5/3, then I'm taking the cube root of it and then raising it to the 5th power. To answer the actual question, x is equal to 5/3. So let's just, I almost said let's beat this dead horse. That sounds cruel. If I wanted to rewrite, now let's kind of divert from logarithms for a second. If I wanted to rewrite this, it'd be a square root, and I'd raise it to the 7th. Now we can make the argument that the 7 goes here. We could also make the argument that the 7 could go inside. Either one is correct. The order would not really matter in this context. There's some where it gets crazy, and yeah, but we're not going to play that game right now with what we're doing. So if I had x to the 101 over 75, I want to pick something that didn't reduce. So I would have the 75th root of x, and I'd raise it to the 101. So I could raise it to the 101 here, or I could say, you know what, it's the same thing as if I do the whole thing to the 101 parentheses if you would like to. Okay? So I teased a little bit about, not teased like joking, but I gave a little teaser for why negative exponents move things, and also want to talk about why fractional exponents are roots, and I just want to give you a quick rundown of that. This part of the video is totally optional. If that the section that we did at the very beginning of the video was like, was good up to a point, and then all of a sudden these negatives popped up, hold your horses. Okay, let's make a chart, and let's use a black marker for this one. So let's pick an easy number. Let's go 3, and we're going to raise it to the 1 power. And then we're going to do 3 to the 2nd power, and then 3 to the 3rd power, and then 3 to the 4th power. And I think we'll just kind of do it like that. So let's make a chart. You can write this or not. You can just stare with your mouth wide open and say, man, this is amazing. And then it'll make sense, okay? So 3 to the 1 is 3, right? This is 9, this is 27, and this is 81, and no one is surprised. So let's look at the pattern in the numerator. The numerator, we're basically adding 1 to the exponent as we go. So if we're going to add 1 to the exponent this direction, let's subtract this direction. So this is 3 to the 0. That'd be 3 to the negative 1, and that would be 3 to the negative 2. Okay? This is going to answer some questions about exponents of 0 and negative exponents. It may not be a proof necessarily, but it does show the pattern that leads you to some understanding. Okay, so numerator, top part of our chart, we're adding 1 as we move along to the right. What are we doing in the bottom part of the chart? Well, we're multiplying by 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay, fine. So we'd multiply by 3 as we go this way. So if we're going to multiply by 3 going this way, we better add 3, sorry, multiplying this way, dividing that way. Division is the opposite of multiplication. Okay, 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is moving the board. 9 divided by 3 is 3. 3 divided by 3 is 1. Pause. 3 to the 0 is 1. Just say it. Okay. 1 divided by 3, that's 1/3. Whoa, whoa, what? 1/3 divided by 3. 1/3 of 1/3 is 1/9, and now we are in territory with negative exponents. Let's talk about this guy real quick. 3 to the negative 2 is 1/9 because I have 3 to the negative 2. It's one big numerator, right? Except for 1. So 3 to the negative 2 is going to go down here. And I'm left with the 1. Not that this 1 came up, but there was an understood 1 there. And there's still an understood 1 there, but you don't have to write them. So I have 1 over 3 squared, which is 9. Okay? Could do the same thing right here. All right, let's talk about, and this again, this part of the video is totally optional, but I'm going to talk about fractional exponents as well, show you where they come from. This one's going to be fun as well. Let's stick with 3. Yeah, let's stick with 3. And we'll do 3 to the 1. 3 to the 2, 3 to the 4, I think that should be sufficient. And then, there we go, we'll do that. Okay, 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 4 is 81, 3 times 3 times 3 times 3 is 81. And so let's look at the pattern. The bottom part of the chart, we are squaring every time. You could say, well, that's times 3. Yeah, I hear you, you're multiplying by 3. You're multiplying by 3, but now you're multiplying by 9. So you're squaring every time. So if I go this way, I'm squaring. So if I go this way, I'm square rooting. So square it, square. Oh, square root of 81 is 9. Square root of 9 is 3. Square root of 3 is that. Okay? And then, well, the square root of the square root of 3. Now things are getting out of control. I'm going to go ahead and tell you it's the 4th root of 3. Because it's the square root of the square root, okay? And it's because 2 times 2 is 4, not because 2 plus 2 is 4. But here's the exponent pattern. You double this exponent, you double this exponent. Okay, so if I'm doubling my exponents as I go this way, double the exponents, then I would do half the exponent as I go this way. Half of 4 is 2, half of 2 is 1, half of 1 is half. So 3 to the 1/2 is the square root of 3. So we kind of gain an understanding now of the fact that an exponent of 1/2 is a square root. And then half of a half is 1/4. There we go.